Oh, right, so the session is now being recorded. So welcome again. Today we're going to start the discussion on power supplies. And well, all electronic systems need a source of power. In fact, any system needs some sort of power. Even if it's yourself, you have to eat food. Your car needs fuel. In terms of electronic systems, most of them require a source of power and a source of DC or direct current power at that. Yes, when you're creating the system or experimenting and so on, you can use batteries. It's good. It's also good for portability as well, but not long term. It's very expensive if you have something. Just think you make an amplifier, you have something that has to operate long term, that the battery supply for it in terms of cost is going to get very expensive. You have some alternative sources of DC power, solar maybe, right? But you need an alternative for night, which needs some means that you have to have some sort of storage, which goes back usually to batteries. Wind, maybe, but inconvenient and definitely not portable. And then you're back to what happens if you don't have any wind. You need some sort of alternative, or again, some sort of storage. And then, well, you could say, okay, well, I don't need batteries. Let me plug it straight into the outlet on the wall. Yeah, but you still need to have the outlet on the wall is 120 volts AC, plus or minus 6%. And you need to get that down to, let's say your laptop works on 5 volts, sorry, right? Or you have an Arduino or some device of that nature that works on 3.3 volts. So you have to go from high voltage AC to low voltage DC anyway. So what we're going to do today is to look at some of the activities that start getting you in that direction, and we finish it off over the next couple of lectures. Right, so the solution is some sort of power supply. It may be an AC or a DC power supply. They are both. All right. In our particular, for our particular purposes, we are going to look at what is known as a regulated DC power supply. All right. And if you look at the little diagram here, and you also have the diagram in your handouts, they broadly speaking, a DC regulated power supply has a couple of blocks in it. Those of you in the signals and systems class this morning will remember me talking about modeling and blocks. So in terms of a diagram, the block sort of layout for a regulated DC supply is that first off, you have a transformer. At the front end, the transformer is going to take the line voltage coming in, right? Maybe 120 volts here. In other parts of the Caribbean, it may be up to 220 to 240 volts, depending on where you are. It's going to convert that from that level to a low voltage, 12, 15, 18, 24 volts AC. At that point in time, you have to convert that AC into DC. And that's where the rectification part of it comes out. After you do that, the DC is it's highly irregular, it's fluctuating a lot. So we pass it through something called a filter that flattens it out and stabilizes it a little bit. And at that point in time, we have what is known as an unregulated DC supply. And then afterwards, we pass it through some electronic circuitry that we call a regulator. And at the end, you get a nice, stable, regulated supply of the voltage you want coming out. Voltage and current, I should say, right? Because both are important specifications. So just some formula to recall. You don't have to memorize them, but by now, okay, so you know the formula for a sine wave or a sinusoidal voltage. Remember, sine or cosine both constitute sinusoidal signals. And then the RMS, how to calculate the RMS, right? Remember, RMS starts for root mean square. So it's an average. You have to square the voltage, take the average, and then take the square root, right? And then in the particular case of a sine wave, the RMS is simply the peak value divided by √2. And of course, the peak value is how high it gets from the zero line or the baseline. And then the average value of a voltage waveform is the area under one cycle divided by the time of one cycle. Right, so again, if you have this signal as V peak sine omega t dt, you can find the area underneath that. Remember, it's a sinusoid, so part is positive, part negative over t. So typically over a normal single sinusoidal cycle, the average is actually 0. Yeah, we're going to see that change as we go through this particular section. So brief review. Some of this you would have done before. Some of this would be, hopefully it would mean you must have done this before. The first part in brief review is half-wave rectification. So you have a transformer. One side of the transformer is the primary, right? You have 115, 120, that kind of thing on the primary side. And on the secondary, it's a step-down transformer. So the secondary voltage is going to be lower than the primary. Right, it typically will have one coil, one secondary coil on the transformer, and the half-wave rectifier uses one diode. Okay, and then there's a little comment here is that a transformer provides something called electrical isolation. In that, let me get up. All right, in that this part of the circuit here, and this part of the circuit here on the other side is secondary, there is no electrical connection. Remember, it's a magnetic connection. You have a coil on the primary and you have a coil on the secondary, and there's no electrical connection. So once you make sure that there's that on the secondary side, here, that at no point in time you have any of the wires coming back to the primary side, attaching to your live or your neutral, then you are electrically safe. There's no way you can get line voltages appearing here. All right? So the transformer, good advantage of a transformer, it gives you electrical isolation. And of course, if there are any questions you want to ask, put up your hand and I'll try to answer it as soon as I can. So after you pass it through the diode conducts for when it's forward biased. When it's reverse biased, it doesn't let any current through it, so the voltage at the output of the rectifier drops to 0. So what you get at the output is this half-wave rectified signal here. Okay? Now, the output is a fluctuating DC voltage. And I'm asking a question as revision. Why? Why is it a fluctuating DC voltage? Yes, Gianluca. No, not quite, Jamal. Yeah, yes, Mr. De Silva.
Yes, are you hearing me?
Yes, I am.
Hello?
Yes, I am hearing you.
Okay, well, basically what the half-wave rectification does, it selects only one half of the sinusoidal wave. So either it would be the positive and leaves out the and it is pulsing it's a pulsating DC because it only have one, pole, one positive. It don't have a positive, well, that's all. And it's pulsating due to the fact that it's, how to say, we don't have any capacitors as yet to how to explain it. You don't have any capacitors to basically smooth out the line. We only have the thing.
Yeah, you answered the part that I wanted at this point. We'll get to the capacitor in a second. But yes, it's
Okay.
fluctuating because
Okay.
it's a fluctuating DC. Yes, Stephen, we'll get to the capacity, which is good that you all at least remembering what's going to happen here. So that because it's rectified, you have a signal that is going, it's starting, it's going up, it's going positive, comes back to zero, going positive, come back to zero. So it's always positive. It's going from zero to some maximum. So that's a DC. It's not going. It's not reversing polarity, and of course, it's fluctuating all over the place. There is an average value though. If you average it over time, you find that the average value is about 0.318 of the peak value. So this whole thing is behaving as though you have a DC voltage of about 0.318, whatever that peak value happens to be. It is DC and it's very irregular at this point in time, right? So we'll come back to that business about the capacitor, which is fine. The next step up is that if you have two diodes and you get another transformer, you can rectify the other half of the sine wave and you get something called full wave rectification. This particular thing, if you have two diodes, then you need a transformer that has two secondary coils, or one secondary coil with an electrical connection in the middle. In this particular case, what happens is that during one cycle, D1 would conduct, and you would get the positive part of the voltage appearing across the load RL. And in the second half, the negative cycle, D2 would conduct, and then RL will see another positive pulsating voltage as well. Because we are using a transformer, again, we are electrically isolated. And then there are bridge rectifiers, and the bridge rectifier uses 4 diodes in a configuration that you should be familiar with, and you see above there. This now gives us full wave rectification with a transformer that only has one secondary coil. It doesn't need a center tap transformer. But to get around the fact that you don't have the second coil or the second half of the coil, you need to add 2 extra diodes to it. This also gives us the full wave rectification behavior, and again, because we have a transformer, we do have electrical isolation. Now, just a general comment on that. There are some, when you go into the lab and in your power labs and so on, you would have met, or maybe even not physically in the lab as yet, but you would have come across a device called an auto transformer. An auto transformer is one where the secondary coil is actually part of the primary. So there's no electrical insulation or isolation, I should say, between the secondary and the primary. It works as a step down, and in fact, it's working. It's like a big variable resistor, except that it's a transformer coil that you're dealing with. And because the primary and the secondary are electrically connected, if you use an auto transformer for a regulated power supply or a DC power supply like what we have here, it means that the ground of the DC power supply is connected to the ground of the mains supply. So so depending on, you have to be very careful in a situation like that, which means that if there are certain things that happen in the power supply, you can't get mains voltage coming across. Or equally well, if something happens on the main side, you can get the power supply being subjected to mains voltage as well. All right. So transformers, I mean, just throwing it in here for electrical safety and so on. Transformers with separate coils for the primary and the secondary give you a measure of electrical safety. Right, so again, we're back to the fluctuating DC, except that this time we have been able to get in the missing half of the cycle from the half wave case, and now the DC value is now about 0.636 times V peak. So we have a little more available DC coming into use. Later on, now we're going to use we will come across this signal again, and we're going to use something called a Fourier series in ECNG2011. Those of you who are doing that, and we will see that this particular signal, you can actually see when you apply the Fourier series, the DC component coming out, and there is some fluctuating AC components there. There are some AC components inside of here as well, strangely enough. The entire behavior is DC because the AC voltages are not going below the negative axis, right? So it's riding, the AC components inside of here are actually riding on top. The AC components are actually riding on top of this DC, so that even though there's a fluctuating value, the negative part is not going below the zero. So that's why the entire thing behaves like a fluctuating DC. Yeah. Right, so we're back here. So the output is a fluctuating DC voltage, and at this point in time, it's not usable for powering most equipment as yet. There are some applications you can use it, for instance, LED lighting, and even some other, mostly lighting applications. In some cases, even some things like driving some DC fans and the like where the fact that the voltage is fluctuating wouldn't be noticed. Remember, it's fluctuating. It's the cycle. Our here in Trinidad, our frequency of the power supply is 60 hertz. Elsewhere in the region, it may be 50 hertz. But whether it's 50 or 60 cycles or hertz, cycles per second, if you're powering an LED, for instance, that flicker you're not going to notice. You're just going to see the LED lit. It's glowing. And unless you film it with a camera and you watch the fluctuation slowly, you will see it. You will not notice anything like that. So what we do to reduce that is that we put a capacitor, as many as somebody else, a couple of people as well pointed out before. So we do that. The capacitor, in fact, is going to work as something called a filter. And so in the case of the half-wave rectifier, the capacitor goes right here after the diode, between the diode and ground, right? So here, technically speaking, on the diagram, should be, okay? And on the on the full-wave rectifier side, right, here should be ground, and here should be ground. Okay, so you could add that to your slides as well, right? And notice where the capacitor is in both cases. Okay, so the behavior of it, and again, some of this is stuff that you would have learned already. The red line is what is the voltage across the capacitor. So at this point in time, I'm assuming that we started off here, right? So that the capacitor charges initially when we now switch on, and it charges up to whatever is the peak value here. It will charge once Vs here is greater than the charge on the capacitor. Of course, minus a little bit for the diode. What is the typical voltage drop across a diode when it's conducting? Anyone remember? Right, good. So at least you remembered something from last year. 0.7 volts typically. So once Vs is greater than the voltage of the capacitor by at least 0.7 volts, the capacitor is going to charge. And it's going to charge until it reaches, well, within 0.7 volts of whatever Vs is. At that point, when Vs gets less, the diode switches off. So the capacitor is left on its own, and the capacitor starts to discharge through the load. All right, if you don't have any load, then this line will hopefully stay fairly level. Okay, but it discharges through the load until the next cycle comes around when Vs goes positive and gets greater than whatever is the capacitor voltage, less the voltage drop across D1, right? And then it charges back up again, and so the process repeats itself. So the capacitor voltage now is this red line. It's a little bit better than the half wave behavior that we had before, but it's still not quite there yet. Right? And of course, how much this line slopes here depends on the value of that load resistor. So if you draw a lot of current from the capacitor, the time constant of the capacitor, which is its value by the load resistor, if you draw a lot of current from it, then the capacitor value is going to drop quite drastically and then have to recharge. And if you make the load big enough, then of course the line gets a little more closer to the horizontal. The general design criteria is that the time constant CR should be bigger than the period T between the charge cycles. All right, and we'll formalize that in a second with an example. So a number of things happen, and this is where that's the behavior. We understand the behavior, but some things we have to be careful with now when you're working with this thing as an engineer or designing something. As the transformer charges and discharges, there is a current here that is flowing in the secondary that is being supplied by the transformer. So there's a pulse current when the diode is not conducting. When the diode is not conducting, of course, nothing flows. But when the diode is conducting, there is a current that is flowing, and that current is going to flow through the diode. It charges the capacitor, and because the capacitor is in parallel with the load, it also is going to send some current the way of the load as well. So if the capacitor is large, remember the capacitor charges through the diode. If the capacitor is large, it's going to pull a lot of current through the diode. So that is part one of the diode rating. The diode has to be able to handle the sort of current that you want to pull through it. And the second thing is that when the polarity of Vs reverses, at the point when Vs reverses, the capacitor voltage here is at plus Vs, and the transformer has gone to negative Vs. So that voltage is now appearing across the diode. So the diode has to cope with a reverse voltage across it of at least 2 times the peak voltage, 2 peak Vs, whatever that is. Yeah? Fair enough? In the case of the full wave rectifier, we have the extra charge cycle here. So because of that, the time for charging and discharging is shorter. The capacitor therefore could be smaller because it has less time to discharge, so you could use a smaller capacitor so the voltage wouldn't drop as much. And then the diode current during recharge, because the capacitor is smaller, it takes less current to charge it back up. So the charge current through the diode is going to be a little bit less. All right. In the case of the diode, the full wave rectifier using the center tap transformer, the same principle applies. If you go back to the center tap transformer, when one of the diodes is off, it is subjected, with the capacitor is charged to plus V peak, and on the negative side you have minus V peak there. So the transformer is subjected to whatever is the peak value of the supply voltage. Yeah, right. I should really have 2 Vs peak like I had before. So you could probably just make a little note here that this here is really supposed to be, these two are really supposed to be the peak values. I'll correct them, but make a notation for yourself. Yeah. So in the case of the bridge rectifier, however, because there are 2 diodes that are operating when the the rectifier is on, you actually find, if you work it out and look at the diagram, and if it's not clear, next time we'll discuss it, that the diodes in the bridge rectifier are actually subjected to twice just the peak value of the supply voltage. Okay, so you have disadvantages and advantages of everything as we're going through. The half-wave rectifier needs the biggest capacitor. It has a PIV of twice the peak voltage of the secondary, and the current therefore is the big through the diode. In the case of the full wave rectifiers, the center tap full wave rectifier using 2 diodes, the capacitance is smaller, the current through the diodes is half what it would have been in a full wave case, but the reverse voltage is the same as it was in the half wave rectifier case. And the bridge rectifier has it the best of the lot in that the reverse voltage on the PIV on the diodes, the peak voltage of the secondary supply, and the current through it, because there are 2 diodes that actually are working, the current is also less. And of course, in both of these cases, the capacitor is smaller. All right? So any questions? We following that? I mean, most of this should be revision, I believe. Yeah, no, maybe? Following. Nice, 1 person. Okay, 2. All right, so let's look a little bit more about the capacitor value, right? If we look at the half-wave rectified waveform, this is after it has been filtered, half-wave, and of course I'm exaggerating it. So what is happening here is that between the charges, of course, the voltage is doing this between each charge cycle, right? So it has a charge, a discharge, a charge, and a discharge. If we just look at this and analyze it a little bit, we define that delta V here, the plus, the sort of between the lowest and the highest, that is what we call the ripple. Okay, so the pulsating voltage after the capacitor now has a ripple, and the size of the ripple is delta V. It reaches some value which is Vp. Of course, because it goes up and down, there's some average value. So we'll call the average value VDC. Okay, so in this case now, we know that the current, we're trying to figure out what's a sort of suitable value for the capacitor here. The current through the capacitor is, well, you remember this from before, C by dV dt. At this point in time, dV dt, we can approximate it. It charges very quickly and discharges. If you look at the graph here for argument's sake, we got almost see, if I look at it, that for all intents and purposes here, this recharge time is fairly short and the discharge time is relatively long. So we can almost ignore here, right? It's exaggerated on this point, but we got to ignore this. And what we say is that basically we can approximate the dV dt behavior as simply delta V, the change in voltage, over the time. All right? And we also know that delta T, the period here, okay, this is 1 over the frequency of the whatever is the sinusoid coming in. Remember how we had that from before. All right, let's go to the full wave. Right, remember this is my signal here. All right, this is the sinusoid here. So this here is the charge period, which is exactly the period of the signal coming in, right? And sorry, and we know that the period is 1 over f as definition. So we can substitute all of that inside of here, and what we get, and change it around a little bit, We get that delta V, which is this fluctuation up and down, is equal to the current that you're pulling through the system, through the diode, through the capacitor, over the capacitance value by the frequency of your supply. Yeah? And then we can do the same thing for the full wave. Actually, just now, before I do that, let me go back here a second. So we have delta V, and what we can say therefore is that our DC value then, the DC value, which is the green line here, right? What we say now is that the DC value, we estimate the DC value as the peak value minus half of that fluctuation. So delta V is going here. A reasonable estimate for this whole behavior here is that the sort of average value of this is the peak value minus half of that fluctuation. Yeah? Fair enough? Yeah? No? Maybe? All right? Fairly straightforward. Maybe. Why maybe? Sorry. Right? Remember, we're trying to approximate the behavior of it. We could get a little more technical inside here, but for engineering work, this analysis will more than suit us. So we have that, and then in the case of the full wave rectified, we have that remember the full wave rectified now, it charges, this charge time now is actually twice as fast as the half wave case, so that instead of delta T is now 1 over 2F. So you put that back, so delta V now is 1 over 2CF. Okay? So if that's the case now, we are now in a position to do a simple design. So without getting complex at this point, design a half wave unregulated supply delivering 12 volts DC at 1 amp and with less than 12 volt, sorry, with less than 2.5 volts peak to peak ripple. So inside of here now, we'll see some of the practical things that you have to think about. The first thing is that you want 12 volts DC. Typically what you would go then is that you would go to your electronics supplier or your parts supplier and so on. If you want a 12 volt DC supply, you will ask for a 12 volt transformer. Why? Because the peak volts, the peak output of the 12 volts transformer is 1.414 times that, which is 16.7 volts, almost 17 volts, right? Which is more than adequate for a 12 volt DC supply. So you're starting off with a raw DC capability of about 17 volts, right? So the first thing, get a transformer that will be able to give you 12 volts at the end, 12 volts DC at the end. Second, you need the transformer. Remember, the current for all of the power supply is coming from the transformer. It's not being created elsewhere. So if the DC supply has to give you 1 amp, typically you want to get a little bit more than that. And the usual thing is to go like 1.5 times that. So that you want a transformer that is going to give you 1.5 amps at 12 volts, typically. They would specify that in some ways. So you can, depending if you're going online and you're shopping from a parts supplier, you could maybe just go on their drop-down list and you look for a 12 volt transformer at 1.5 amps, or sometimes they give you the VA rating of the transformer. The VA rating, of course, is the current times the voltage, just the product. And that now, if you know it's a 12 volt transformer, you have to work out the current yourself. Right? So part one, you have to get a transformer, and this is a reasonably good way of getting it. And of course, there are different sizes and shapes of transformers that will do exactly the same thing. We wouldn't get to that now, but we'll talk about it in time to come. The next thing now is at the diode. So part one was the transformer. The next part, we need a diode. So we need a diode. If it's a half-wave rectified supply we're dealing with, it's going to have to handle the peak voltage twice the supply peak voltage. Right, this peak voltage, as we said, is about 17 volts, so the diode has to handle about 34 volts reverse. So you go to the spec sheets. You go to your suppliers, or you go to the spec sheets, or a data book, and if you have one available, in electronic form or anything so, and you now look for a small rectifier diodes with a peak inverse voltage of about close to 33.9. Again, you want a safety margin, and if you look, you'll see that they come in some chunks. So you wouldn't get 34, you wouldn't get 35, and in any case, just to be safe, you wouldn't use 34, 35 volts just in case, right? You would give it at 50, because if, for instance, the transformer is giving you 12 volts out, assuming, let's say, that the primary is giving you 120 volts in. There are times and there are places in Trinidad, for instance, where the voltage may go up to 124 volts. If the primary goes up to 124, the secondary is going to increase from 12 to something. If it increases to, just for argument's sake, 13 volts, then the twice the peak is going to be 13 by the 2, which is going to get you over 35. So you try to be a little bit, you always give yourself a safety margin, good design as well. Right, so we now have two things. We have a transformer to handle the current and the voltage. We have a diode that will handle the voltage going through it. And of course the current, you would look for the current rating, of course, because it has to handle at least 1.5 amps probably. Yeah. Now to the capacitor. So from the capacitor, the design question is asking us to get 2.5 volts peak to peak ripple. So delta V is 2.5 peak to peak. That is equal to I over CF. I is 1 amp. C is what we want to calculate, and F, we are assuming that we are 60 hertz signal. If you're elsewhere in the Caribbean, and it's 50 instead, well, of course, you substitute inside of there. If you solve for C, you get C is that funny number, 6666 microfarad. You're not going to get that value. Okay? Capacitors come in standard values with reason. It's difficult to manufacture values, all the values that exist. Remember the discussion this morning in signals, those of you who were there, about continuous and discrete time? Well, this is kind of discrete values. You can't have a continuously variable capacitance values that you can just go and get. So they're going to do now 6,666 microfarads. If you look at the standard capacitance values that are available, right, you're going to see that you will get something 6,800, and that funny symbol looking like a candle is actually supposed to be a micro. I don't know what happened there, but in your handout it's there, right? There we go. That is supposed to be micro. Right? So the closest standard value is going to be 6,800. And then there's another little spec that the specification that the capacitors come with, which is the working voltage. All right? That is, again, is there to help when you're doing designs and so on. You have to bear in mind, and this is an aside, if you're doing this commercially for argument's sake, money, every component, every cent that you spend on a component is going to add up in the end. You think about it, if you're making something, and let's say you're a manufacturer, and this is part of a simple wall adapter, something plugging into the wall to power something. If you save a few cents and you're making these things by the millions, which is what they do, right? A few cents by a few million translates into a lot of money. So what you would normally do as a designer, you would look to see what is the sort of closest working voltage that is available for you. And if you check this one, we are delivering, we want to deliver about, we want to deliver 12 volts here. But if something really happens, we know that the system can deliver 17 volts at a raw value. So therefore, you want a capacitor that can handle at least 17 volts and not barely handle the 17 volts. So we look for one where the working voltage is a little bit higher, and 25 volts is what you would come across. So the design at this point in time is completed. We have the transformer. We're catering for 1.5 amps at 12 volt secondary. We have the diode. The diode is going to carry the same 1.5 amps, and it has a PIV of, what did we say, 50? Right, a PIV of 50. And then the capacitor, we're going to use a 6800 microfarad capacitor, and we're going to have a working voltage of 25 volts. Right, so your design, at least at this point in time, is now complete. Right, and your homework, once we finish the discussion here, your homework is to repeat this for the full wave and see what the values look like. Right, so back to the question that was started off, that was put very early before we started the class. Is the phone adapter regulated or unregulated at that point? What do you think? Right, so it's back. It is regulated, and it isn't is what we've done here today is even better than that, right? Which is the next part of the conversation. So, any questions? Some of this, most of this might have been revision for you. Some of it, I try to get into a little bit of the considerations that you have to consider. And one of the things I want to do as we go through, sometimes we'll spend a bit of time going into detail where the detail is required. In other cases, we'll kind of start off with a design problem or something to analyze. And as we go through the analysis, we'll pick out how we calculate this and how we calculate that, and take the discussion from there. All right, so it's going to be a variation of things. The handout that I gave you, as I said, it is from what Professor Giff would have written for the class to give a lot of background stuff, and it does have a lot of useful information in there. So you can take your time and read it, a lot more than what we will discuss. So maybe until we finish the topic, then you could kind of highlight the sections that were there. And then in between, we could look at other things. What I would like, though, from the course generally, is that as we go through, by the time we reach the end of the course, you would know how to design power supplies, you would know how to design certain types of waveform generators and certain types of amplifier circuits and the like. Don't forget it, don't compartmentalize, so that next year when you're in a micro P class, or the following year when you're doing your final year project and you have to sit down and design something now, that you designing it and you forgot, wait a minute, there's a formal way to design these things, so that everything that I have in my final design, I'm able to justify, and I know that once I put the design down, it will work. All right. During the course of this thing as well, too, in between, we will use multisim. I just have to activate it on this, and let's see what we could do. So in between, we could try things, right? It's sort of like an online practical session. If I can't do it in class, what I will do maybe is to record it and have it available so you can see and try. And feel free to experiment, right? Some of you all, you may have been introduced to multisim since last semester. So it's there's nothing wrong in playing around with these things and just seeing for yourself. The simulation environment works fairly well, and at that point you can actually experiment and see what if, you know. So any questions? Any lingering questions at this point? Yes, Mahendra.
So I kind of have a question, right? I'm not sure if I don't know if it really making sense, but okay, so like we have capacitors and stuff, right? Does it have like different brands in capacitors that will give you like better results or no? Like always have
Yeah,
different brands in like shoes and whatever and things, right?
yeah. Yes, absolutely. Just think about these things. They're manufactured all over the world. They made in China, they made in Taiwan, they made in the States, they made in all sorts of countries around the place. Um, yes, and recommending a brand is like recommending a pair of shoes. They're all over the place. What engineers would do and design engineers would typically have to do is to go to the data sheets for the particular brand. So if you are looking for a capacitor, just for argument's sake, and you go on to like for instance, we in UE we buy a lot of our components from a company called DigiKey, which is Digikey. You could probably Google that. If you go on there and you look for a capacitor, just for argument's sake, you're going to see thousands of them come up, and you're going to see all of the brand names. The brand names, some of the brands have reputations, others less so, and you could get that from the sort of the cost of it, the country of origin sometimes. All right. If you're doing things like, for instance, medical applications where extreme reliability is an issue, then the reliability takes precedence over the cost. So what you're going to do is to go on and source the most reliable capacitor irrespective of the cost of the device, right? And that, I'm not too sure what brand that might be. A general purpose power supply for home use or for low grade production ones and so on. You know, you have to cater that it will last, okay, it might last a few months, it might last a year or so. So you put in some components that will give you like that. All right. That, what you talk about is a very deep question in terms of engineering design, okay, balancing the cost versus the reliability, versus the reputation, right, and versus the application. There are a whole bunch of things inside of there, right, and that is something you could do an entire course, you could do a whole program on manufacturing and manufacturing design, right, and perhaps and sometimes we might be able to incorporate that when we get a chance, but long sort of answer to a very simple question, Mahindra. I don't know if that sort of satisfies what you're asking.
Yeah, and I have like one other question, right? So I have
Mm-hmm.
different brands, right? It made up of different like components, like our transistor is made up of silicon atoms and boron
Mm-hmm.
and whatever, right? So the capacitors have like different capacitors, the different brands have different atoms in it and stuff, and that will affect like the how long it will last and yeah, does it have like different stuff or all of them have the exact same stuff on?
All well, you remember capacitors, they are polarized capacitors, they are non-polarized capacitors, they are electrolytic capacitors, there is ceramic capacitors, surface mount, there are a whole variety of them. Generally, within a particular family, like electrolytic capacitors, the ones like for power supplies, they all essentially are made the same way, which is the capacitance plates. If you remember from your physics what a capacitor is, or even from early electronics or electrical engineering, a capacitance is two plates and a dielectric. The plate, quote unquote, in most of these capacitors are sheets of foil, aluminum foil. So you have two sheets of aluminum foil and they are separated by the dielectric material. In the case of the electrolytic capacitor, the dielectric material is a polarized, is an electrolytic gel. And when you connect the capacitor in the right way, right, the positive to the positive terminal, the negative to the negative terminal, the polarization creates the dielectric and you get the capacitor behavior. If you reverse it, then the dielectric becomes conductive and you short circuit the capacitor. And I was making a joke in the last class about blowing up capacitors and so on, right? That's what happens. So within a particular family, all of the capacitors will be made more or less the same. right? The more expensive capacitors would, of course, use more reliable material or better grade material. Again, for things like military applications, for instance, they are designed to operate at a higher temperature. For medical applications, they are designed to have extreme reliability. Same thing for the aerospace industry. Okay, so the design is again the same across the families, more or less, but the quality of the materials would be different. Yeah. But it's something it's not, well, yeah, Jared, and that's half the fun too. And you can't go through electrical engineering and not blow up something, quote unquote. I mean, you know, you have to burn something or smoke something, or burn your finger or something like that. But yes, Mahendra, there is a selection of possibilities, but within the particular families, they tend to be made fairly similar. And that is also because you remember as well too, if you have to substitute one brand for another, let's say there's an issue where you're manufacturing something and you have two particular brands that could possibly work in your design. The circuit board has a particular space for the capacitor to occupy. So if the capacitors are made differently, then it's going to make it very hard to swap one brand for another. So in fact, that is standardized to some extent, all right, within the particular type of capacitor. But the manufacturers have their own little tweaks that they will do, which is their own secret that will make it work better than another one. Yeah.
Okay. Yeah.
But it's an interesting discussion. It's something that we could, as we come along, we will see some examples of that as we go forward too, hopefully. All right, so any other questions? All right, so we will end the class here today. I'll stop the recording now. Right, let me stop the